All right, let's take a quick little glimpse at the equation sheet here. On our energy cheat sheet, we don't have anything in here yet for a dissipative energy for an equation. And a lot of times that'll be calculated based on the frictional force, right? There's some friction, so some energy is going into warming things up. Um, and that'll all kind of be related to this. So a couple of things to point out on the equation sheet, and we'll get more practice with this later when you need it. We got a couple of things here from earlier on. This is telling us that force is the slope of a graph of momentum versus time. So if you had a plot of momentum versus time, the slope on that's going to be the force. That's kind of like what do I want to say? So force is the derivative of the change of position, or sorry, change of momentum um, with respect to time. And then here we have the impulse, and this is basically telling you that the impulse is the change of momentum, and the change of momentum is the area bounded by a graph of force versus time. Okay, and that's stuff we dealt with earlier in the year. So if you had a plot of force in newtons, time in seconds, and it had some kind of shape to it, some force F here goes over like that. This area would have the units Newton seconds. That's not Newton meters, it's Newton seconds. So if you take Newton, kilogram meter per second squared, and multiply it by seconds, you're going to get kilogram meters per second. That's equivalent to Newton seconds. Okay, that's dealing with momentum and change of momentum and impulse, all that jazz. Now, though, we're dealing with Newton meters, and so it's kind of a similar idea. You've got a graph of force versus distance, force in newtons, and let's say distance x here in meters. It's a similar idea. So I've got some force F, it's acting over some distance x. This area, that's going to be the change in energy, and that would have the units Newton meters. Okay, and it could be a graph that goes like this, and then it's a triangle. Force is changing with position like in a spring, but again, that area is Newton meters. Well, that shows up on the equation sheet right here. Okay. And the delta E thing, that's a newer twist to them. I think I made enough complaints that they recognize that we really should just be thinking of that area as the change in energy. But they like to throw a word on it. They talk about it as the work done on a system. Okay. So in other words, this would be energy being transferred into a system. Um, and they're talking about that in terms of F dot dr. And this dot has a special significance as well. When we're doing multiplication with arrow quantities, with vectors, there are a couple different ways that we run that. One of those is called a cross product, and I don't have any examples on here. We'll come around to that eventually. And one is called a dot product. And a dot product here is interested in how collinear or coplanar these arrows are. Collinear. So a Mr. Harding algebraic way of thinking about that is effectively it's saying that the change in energy is equal to the F, the force vector, times we would probably just use delta X, the change in position, or I'm kind of using that interchangeably with distance here, times the cosine of the angle in between those things. So let's look at a couple of examples here. Let's say I've got a box being dragged across the floor. Let's make this a box, mass M, and there's some kind of a tension force T acting on this thing, and it's going to move a distance here delta x. Okay. So for our purposes, if we want to calculate the change in energy due to this force alone during this time, then I'm simply going to take Ft times delta x times the cosine of the angle in between those things. And this is kind of why they're using r here as a position vector, because this arrow would represent my displacement here. Okay. So as a vector r, those arrows are both pointing the same direction. They're parallel, so the angle between them is 0, and as everybody knows, cosine of 0 equals 1. So when the forces both point in the same direction, the change in energy is at a maximum, and it is effectively just Ft delta x. That would be finding us the change in the energy due to the tension force here. There are other forces acting. There's also a gravitational force pointing down like that. Okay. And if I want to look at the change in energy due to the gravitational force here, I would take Fg times delta x, and the angle between this vertical gravitational force and this horizontal change of position is 90. Okay. And cos 90 is 0. So now I would have Fg delta x times 0. There's no change in energy. The gravitational force here isn't transferring any energy to the box in this situation. Some would say because there's no distance moved in the direction of that force. Okay. And then you could also, let's say there's like a frictional force here. Okay. So I've got some friction going this direction, Ff, and that's pointing 180 degrees opposite of the arrow that represents the change in position for this thing. So Ff delta x, the angle there is going to be 180 degrees. Okay. So,
are you in a meeting or something?
No, I'm just screencasting. Give me a second here. I can pause it. I hate that I don't have a quick button on this. All right, where was I? So I think I'm talking about frictional force here, and the angle between the frictional force and the delta x, right? That's, I did say that, 180 degrees. So I go cos 180 degrees. Cos 180, anybody? Yep, -1. So this is going to be like, this is like a way of energy working out of the system. So, right, if you had something that had some kinetic energy and it's experiencing friction, you're going to have a decrease in the energy stored in its motion. That's work being transferred out of the system by friction. So this, again, would be negative Ff delta x, or however you want to think about it. Okay. But yeah, you could kind of put this in for the E-dis equation. It's going to be a loss is a bad word to use here. A decrease in energy. It's energy transferring to thermal. So things slow down when that happens. So back over to the energy cheat sheet, and yeah. F delta x. And again, that friction's typically going to be parallel to the surface, motion's along the surface, and it's pointing opposite the direction of motion. When this is another important understanding about this is going to be kinetic friction. Okay, kinetic friction, or sliding, and that's how you get motion along the axis of the force, so to say. If it's static friction, you're not what do I want to say? Let's not paint ourselves in any corners there. But most often you're talking about kinetic friction here. I'll just leave it like that. And then the other example like this that comes up is if we're talking about circular motion, and I did talk about this in one of the classes today, but things are moving around in a circle here. You've got your velocity directed like that. And then let's say this is like the stopper on the string. So it's going to experience a tension force like that. Okay, so here's Ft. These are not both forces. One's a velocity, one's a force. But I'm pointing that out to show you that the force is perpendicular to the motion. Okay, so even though the velocity vector is constantly changing direction, the tension force is as well. It's just that it's always pointing perpendicular to the velocity. So in that sense, you could kind of recognize the whole cos 90 thing. Long story short, the force that's responsible for making this thing go around in a circle here is not changing the energy of it. Okay, if the force is perpendicular to the motion, then there's no change in energy. It's not speeding up, it's not slowing down, so there's no change in kinetic energy here. All it's doing is changing the direction of it. Okay, so that's hopefully a little bit of an insight into this other equation that matters on here. And then you'll recognize some other things on the sheet. I don't like the letter representation here. K equals 1/2 mv squared, and then there's some other letters used for some other injuries. They're all E. This is stored in motion. Like, come on, College Board, get your act together. All right, that's longer.